Okay, assalamu alaikum. I have made this video at the request of my students who have asked me to help with their revision process. So it only gives me great pleasure to be helping out with that. Um, the only thing I will say is obviously with these revision videos, the best thing to do is to follow along. So I hope you have your pen ready and I hope you have your notes ready because the only way to learn is by doing it yourself. So there we go. Okay, so just a few points I want to talk about before we start. This grade 8 science midterm review is not the complete comprehensive revision. This revision is not enough on its own. Okay, I have to stress that point. This is not enough on its own. So you are expected to go through the book, you're expected to go through your notes, you're expected to go through any other notes that your teacher may have given you, okay, and any other worksheets that your teacher has given you. It is a midterm exam after all. So what we expect from you is that you go through the notes and you go through the books. Now this should be this should be a good review that covers most of the topics. And obviously that's the whole point of it, is that it covers as many of the topics and as many of the keywords that you need to know. However, I must say it's not enough on its own. Okay, right, and with that out of the way, let's carry on. Let me start by talking about the exam structure. So the exam is going to be divided into three parts. The first part is going to be part A, where you have matching vocabulary, and part B is going to be multiple choice questions, and part C is going to be problem solving. Okay, and so for example, part A, you'll need to be familiar with these words and any other words, as well as any other words in the book and the notes that your teachers told you about. Okay, but for sure this is the minimum that you need to be familiar with. Okay, and this comes straight from the book. So they're basically the highlighted words at the beginning of the chapter, and this is so you need to be familiar with them. And when I say familiar with them, I don't mean that you have to learn them off by heart, but what you need to know is you need to recognize them, you need to understand them, so that when the question says what is the atomic number or what is the atomic mass, you know what it's talking about. Atomic number means number of protons, atomic mass means number of protons as well as neutrons. So you need to be able to understand what these mean in order to answer the questions. Okay, so you need to be familiar with these ones and any others that are in the book. Okay, so I'm going to start by talking about certain topics, and I'm just going to go through it, and then I'm going to jump straight into answering questions. And my advice for this exam is as follows. Go through the video and see how you do, and it's going to be obviously a slightly longer video than I normally post, because obviously it's going to include some questions as well. But if you feel like you need a bit more help, then obviously you can go and research those topics that you need a bit more help with. I wouldn't spend countless hours just going through every single thing. What I would do is I would make a mental note or an actual note of the topics that I'm struggling with, and I would go back and start with these first. Okay, so let's just go through it and see how you get on. So contact and non-contact forces. So basically what we mean by that is forces are things in, well, what we call an interaction between two objects. Okay, and forces are measured in newtons. Forces, you can say a force is a push or a pull. Forces can either be contact or non-contact, and basically if they touch, if the two objects that are applying forces on each other are touching, then we call that a contact force. Contact means touching. And if they're not touching, then we call that a non-contact force. So examples of non-contact forces, like the obvious one is gravity, obviously, or weight. See, if I let go of this and there's nothing attached to it, it still goes down. How does it go down without anything grabbing onto it? It's because it's a non-contact force. So gravity or weight is a non-contact force. The other one is magnetic forces, and obviously these are not contact forces as well, because you can attract things to a magnet without using any forces or strings or anything like that. And the third one is electric forces or electrostatic forces, and these are very interesting, because if you for example take a ruler and you rub it against your hair and you go near a stream of water or you go near some paper, you'll see that the paper goes towards the ruler. Now that's because of electrostatic forces, negative charges and such. Okay, so those are the types of non-contact forces that you need to be familiar with. And if you need more information, as I said, you need to go back and watch that video, or you need to research and ask your friends and so on. And by all means, you can always ask your teacher as well. And some types of contact forces are here. There are others as well. Okay, so what is the difference between an endothermic and an exothermic reaction? Simply put, an endothermic reaction is one that absorbs energy or that absorbs heat from the surroundings, while an exothermic reaction is one that gives out heat and gives out energy to the surroundings. So an example of an endothermic reaction would be cooking, for example, because you're giving it heat. And the easiest way I find for students to understand this is if you put yourself in place of the object that you're trying to analyze. So let's say, for example, ice, right? Let's say ice melting. If I imagine for a second that I'm a block of ice and I want to melt, what can I do to melt? Well, I need to absorb some heat. So that automatically tells me if I'm absorbing heat, that's going to be an endothermic reaction. What if I want to boil? What if I'm water? I'm water and I want to boil, right? If I'm the water in liquid form and I want to boil, I need to absorb heat. So that's endothermic as well. What about if I'm gas, like I'm steam, right? And I want to condense. So I'm turning from gas to liquid, right? I'm turning from gas to liquid. The way to think about this is which one has more energy, gas particles or liquid particles? Well, gas particles have a lot more energy than liquid particles. And so in order for me to turn into liquid, I need to lose heat. I need to lose energy. So that becomes exothermic. What about liquid freezing? Okay, so we've got liquid and the liquid wants to turn into ice. Okay, so if liquid wants to turn into ice, what does it need to do? Well, let me think about this for a second. That's ice right there, and ice is very solid, and ice is very cold. And liquid is also cold, but it's not solid. What about the amount of energy in the particles? Which one has higher energy? Well, the liquid particles have more energy, okay? The gas particles have even more energy, but then the liquid particles have more energy than the solid particles. So in order to go from liquid to solid, those liquid particles have to lose even more energy to become solid. So they have to give out energy. So this also becomes exothermic. Okay? Exothermic. So freezing water is an example of an exothermic reaction because you need to get rid of that heat. Okay? Remember, you're putting yourself in that object. You're the water and you want to freeze. You have to give out heat. Right? What about burning wood, like logs of wood? Okay, and we're burning some wood. Is that exothermic or endothermic? Okay, now we have to put a little bit of energy at the beginning, like basically like a lighter or something. So to say, for example, if I light something on fire using a lighter, okay, I'm giving it just a little tiny bit of energy, but for the most part, the energy is potential energy. It's stored energy within the wood. And so once the wood starts burning, it gives out a lot of heat. So that's also exothermic. Burning anything is pretty much exothermic, okay? And an exothermic reaction is one where a lot of heat is given out and light as well. So, so light and heat. Not always light, but certainly heat and energy is given out, okay? So exothermic reactions, heat is given out, sometimes light is given out. Endothermic reactions, heat is absorbed. Another example of an endothermic reaction is photosynthesis. Plants take energy from the sun, they take it in, so that's endothermic, and so on and so forth. Okay, what are the properties of metals and non-metals? So you need to be familiar with these as well. Metals are lustrous. Lustrous just means shiny and reflective. metals are shiny and reflective. And if I show you something right now, you can tell me whether it's metallic or not just based on its looks. So here we go. I've got those nail clippers over here. Now you can tell immediately that they are metallic. Now the reason you can tell it's metallic is because it's shiny and it's lustrous. Okay, they are shiny and lustrous. So that's what we mean by lustrous. They are reflective, they are shiny. Whereas non-metals are dull, and dull are things like this. Okay, you can tell it's dull, it's not very shiny, it's not very reflective relative to the metal. Okay, so metals are shiny, non-metals are dull, which is the opposite of shiny. What else do we have? We've got metals are good conductors, and that goes for both electricity and heat, which is why we use metals for conducting electricity, and they're also used for conducting heat. So metals are good conductors of electricity and heat. That's why frying pans are made of metal. That's why pots and pans are made of metal, because they conduct heat, which helps with the cooking, obviously. Now, some of you at this stage might be going, well, there are some kitchen utensils that are made of glass or Pyrex. And that's true, but that's an exception. And for the most part, we're talking about generally speaking. So generally speaking, metals are lustrous. Generally speaking, metals are the good conductors of heat and electricity. Generally speaking, metals have high melting points. So what that means is metals are solids at room temperature, with the exception of mercury. And gallium has a low melting point. But for the most part, metals are solid at room temperature, whereas non-metals, which are on the right side of the table, of the periodic table, they tend to be gaseous or liquids, right, at room temperature. So things like noble gases, they are gases. Things like fluorine and chlorine and bromine, these are all gases at room temperature. So metals tend to be solids. They have high melting point. What that means is they don't melt until the temperature is really, really high, whereas non-metals, they melt quite easily. Metals are also malleable. What that means is metals can bend easily. So I've got a paper clip over here, and as you can see, I can bend it quite easily. That's called malleable. Non-metals don't tend to be malleable. Non-metals tend to break. If I try to bend them, they tend to break. Now, obviously, there are exceptions to the rule, but for the most part, non-metals break. They brittle. They don't bend, they break. So I want you to think about glass, for example. If you try to bend it, it breaks. So that's what we mean by brittle. Brittle is the opposite of malleable. Brittle means it shatters when you drop it, okay? Or it doesn't bend, it breaks. What about ductile? Ductile means it can be drawn into wires. So if you look over here, I've got a type of metal. This is lead, okay? So it's... Here we go. So it is drawn into wires. Okay, so I can do that with metals. Metals can be drawn into wires, whereas I can't really do that with non-metals. Okay, it's not something that I can easily do. So there you go. There are always exceptions to the rule, obviously, but for the most part, metals can be drawn into wires, and that's called ductile. Metals are malleable, which means they can bend. Metals are solids at room temperature because they have very high melting point, and so on and so forth. And don't worry about this one so much. I don't want you to be concerned with that one. Just don't need to worry about it for now. Okay. And here we come to properties of ionic and covalent compounds. Excuse me while I sip on my karak tea. Delicious. Right, properties of ionic and covalent compounds. We have two types of compounds. Once again, this video isn't about explaining things in great detail. It's about answering questions and covering them very briefly. So if you would like to go and find out a bit more about the properties of ionic or covalent compounds, go and watch the original video that I've made back when. Alternatively, you can always go and look it up or read the chapter in the book. But for now, we're basically just covering the basics. So ionic and covalent compounds, what we mean by that is ionic compounds are between a metal and a non-metal. So ionic compounds are between metals plus non-metals. with ionic compounds, there is a give and take relationship. So the metals tend to give electrons to the non-metals who accept the electrons. So the metals tend to be electron donors, or they give electrons, while the non-metals are electron acceptors, or they accept the electrons. And what this does is it makes the metal positively charged and it makes the non-metal negatively charged, because this guy just took an electron. And when this becomes negatively charged and this becomes positively charged, what happens then is they attract to each other just like a magnet, and they form an ionic compound. So this is how you form an ionic compound. They're very, very strong compounds. They form between metals and non-metals. Ionic compounds tend to form crystalline structures. So that means is like things like salt, for example, is an ionic compound. And this is what they look like. They look like crystals, okay? Unlike covalent compounds, which that's not the case for covalent compounds. Ionic compounds have very high melting and boiling points. So what that means, they don't melt even if the temperature is very, very high. And if it helps you understand this better, like just think, metals have very high melting points and ionic compounds have metals in them. So that's partly why they have very high melting points. It's also got to do with the attraction between the metals and the non-metals. But if it helps, for sure, ionic compounds have very high melting points. Covalent compounds have lower melting points, generally speaking. Both of them don't conduct electricity. So both covalent and ionic compounds don't conduct electricity at normal conditions. But if you dissolve ionic compounds in water, or if you melt them, then they conduct electricity just fine. So things like salt, for example, if you put it in water and you dissolve it, then it conducts electricity just fine. Okay, so ionic compounds can conduct electricity when they are dissolved in water, or when they're melted, but covalent compounds don't conduct electricity at all. Okay, let's move on. Okay, so next we come to chemical and physical changes. And obviously there are two types of change. So we have a physical change and a chemical change. A physical change is one where no new substance is made. That's the simplest definition. A physical change is one where there's no new substance. We basically have changed the state, the shape, whatever, but we haven't made a new substance. So cutting paper, for example, that's still paper. Melting ice, that's still water. Boiling water, like turning it from liquid to gas, that's still water. Chopping wood, that's still wood. So no new substance is made. With a chemical change, a new substance is made. So for example, when you're baking bread, you cannot get the dough back. You've now made a new substance. When you're grilling a steak, you can't get the meat back. When you're burning wood, you've now made a new substance, ash. You can't get the wood back. Rusting is an example of a chemical change. Digestion is an example of a chemical change. So all of these are chemical changes because you've made a new substance. So when a new substance is made, it's a chemical change. When no new substance is made, it's a physical change. Okay, let's talk about solutions, colloids, and suspensions, because this is another one that students find a little bit confusing. So I want you to listen in very carefully. So we've got an umbrella of mixtures. Mixtures are basically when we mix two or more substances together that are not chemically bonded. So no new substance is made, I've just mixed them together. So an example of which would be if I mix salt and sugar together, or if I mix sand and water. I've not formed a new substance, I've just mixed them together. So I still have the sand and I still have the water, and I can separate them, right? So that's generally what a mixture is. Now, there is a bit more to it. So we're talking about liquid mixtures here. And there are three types that I want you to know about. So first one is a solution. And a solution is a clear liquid. And if you'd like to know more about this, please go back to the original video that I've done. And I remember like using my laser to show you. But generally speaking, a solution is a clear liquid. Light goes through it. A solution is homogeneous, which means it is made of there's one substance in there, and it's tiny, and it's everywhere, and it's distributed evenly. It's not gonna settle at the bottom of the beaker. It's going to be distributed evenly across the whole beaker. Light's going to go through it just fine, and it's going to it's homogeneous, which means it's clear, right? So apple juice is an example of a solution. Tea is an example of a solution. That's black tea. Um, what else? Seawater is an example of a solution. Sugar and water that's dissolved, sugar that's dissolved in water is an example of a solution. So solutions are clear. Okay, you can see through them. If I put a paper on the other side of a solution, you can see it. Light goes through just fine. What about colloids? Colloids are actually heterogeneous. Okay, colloids are heterogeneous. They're made from more than one substance, and those particles in the colloid are slightly bigger than the solution, and they're not dissolved in. They are distributed evenly. They're distributed everywhere, and they're distributed evenly, and it looks homogeneous because sometimes it looks like it's the same color, like lentil soup or like milk, but in reality, it's actually heterogeneous. Okay, now with colloids, they don't suspend, so it doesn't separate, right? So it stays the way it is. It's mixed in properly. It's distributed evenly, but it doesn't allow light to go through cleanly. Now, what I mean by that is light goes through, but it scatters the light. Okay, so you can't really see from the other side. If I put a piece of paper on the other side of a colloid, you can kind of make out that there's like a light source, but you can't actually see what's on the paper. So it's not the same as a solution that's completely clear. So a solution is completely clear, whereas a colloid is not, and it doesn't allow light to go through, and the particles are distributed evenly. Now, the last one I want to talk about is suspension, and suspension is the easy one to explain. Suspension is the one where if you leave for a while, the particles separate from the liquid, right? So an example for example, oil and water. If I leave oil and water for a while, even after I mix them, the oil will go on top of the water because the oil will separate from the water because it's different density, and that's what we call suspension. Another example is sand and water. So if I mix sand and water, it might look like a mixture, it might look like a colloid, and I can't see through it, but if I leave it there for half an hour, you'll see that the sand goes down and the water stays on top. And that's what we call a suspension. They literally suspend from each other. And with a suspension, another example is like orange juice with the pulp. Okay, so if you leave the orange juice with the pulp for a while, the pulp will settle at the bottom and separate from the orange juice, and that's why they say shake it well, because it's a suspension. A suspension is where the particles separate. Solution is where it's absolutely clear, and a colloid is one where you can't see through it. It looks like it's one color, but you can't see through it, and it doesn't settle. It doesn't separate. Okay, let's keep going. All right, so here we've got some examples of questions, and what I'm going to do is I'm going to go through some of these questions, or should I go through? Yeah, let's go through some of these questions. Calculate the speed of the car during the first 10 seconds. Okay, so how do we calculate the speed of the car during the first 10 seconds? We've got a distance time graph, and we're asked to calculate the speed of the car during the first 10 seconds. First thing I need to know is look at the graph and realize that 10 seconds is right over here. That's 10 seconds. So that is 10 seconds, okay? And I need to calculate the speed of the car. Now, the speed of the car is going to be rise over run, because we know that speed equals distance over time. Now, what I'd like you to do is I'd like you to pause the video and try and attempt to do these problems yourself, and then check your answers with me as I go along. So calculate the speed of the car. It's going to be speed is equal to distance over time, which is going to be 200 meters divided by 10 seconds, or because see, that's 200 meters, that's the distance, and that's the time, 10 seconds, and that's going to be 20 meters per second. Don't forget the units. For how long did the car stop? So the car stopped over here, okay, and you can see that the car stopped for 20 minutes, or 20 seconds. 20 seconds, okay, because it stopped from 10 all the way to 30. So it stopped for a period of about 20 seconds. 30 minus 10, which is 20 seconds. What is the speed of the car on its journey from C to D? From C to D. So first of all, once again, it's rise over run. So that's going to be that over that. So that's going to be 300 meters because it's 500 minus 200. And that's going to be 30 seconds. So it's going to be speed is equal to distance over time, which is 300 meters divided by 30 seconds, or 10 meters per second. Okay? On which part of the journey did the car travel the faster or travel the fastest? Obviously, since we've worked it out, we know that A to B is the part of the journey that it traveled the fastest. Also, another way of doing it, even if you haven't done the problem, another way of doing it is by looking at how steep the graph is. So if the graph is this steep compared to that, or compared to this is the fastest. All right. What is the average speed of the car for the whole journey? The average speed for the whole journey is going to be the total distance divided by the total time. Total distance divided by total time, which is going to be 500 divided by 60 seconds. 500 meters divided by 60 seconds, which is 500 meters divided by 60 seconds, which is about 8.3 meters per second. Okay? Because just total distance divided by total time, that's how we get average speed. Let's move on. A car starts from rest and reaches a speed of 20 meters per second in 5 seconds. What is the car's acceleration? So we're looking for acceleration here. Acceleration has a formula, and you will be given the formula. Acceleration equals final speed minus initial speed over time. So final speed minus initial speed. Initial just means beginning. So beginning speed over time, which is going to be, since we start from rest means 0. Okay, so it's going to be 20 minus 0 all over 5 seconds. It's going to be 4 meters per second squared. Don't forget that the unit for acceleration is meters per second squared. A car increases its speed from 20 meters per second to 30 meters per second in 5 seconds. Calculate its acceleration. So once again, acceleration equals change in speed or change in velocity over time. Now, some of my students would have seen me do this. Okay, and that's perfectly fine. That just means final speed, and this means initial speed, and this means time. Okay, so that's all that means. So it's exactly the same. But you don't have to write it like this. You can even write it like this, like final speed minus initial speed over time. So it doesn't matter as long as you know that it's the final speed minus the initial speed over time. So it's going to be so it's going to be 30 seconds, which is the final speed, minus the initial speed, which is 20, over 5 seconds. So that's going to be 10 over 5, or 2 meters per second squared. Okay, we've got some multiple choice questions to do. What determines an element's position on the periodic table? What determines an element's position on the periodic table is its atomic number, or the number of protons. Okay, atomic number is equivalent to number of protons. Okay, and that's really the ID of the atom. Which of these is an example of a nonmetal? The one nonmetal that I can see is going to be neon, and that's, as you know from the periodic table, neon is actually a noble gas as well. What type of bond forms between a metal and a nonmetal? The type of bond that forms between a metal and a nonmetal is one of give and take, one of ionic nature, ionic bond. And it's important at this stage that I say there is ionic bonds, so ionic bond, and there's also something called a covalent bond where sharing happens, and that's between non-metals. But covalent bonds are also known as molecular bonds. So molecular bonds and covalent bonds are the same, okay? And these happen between nonmetals. Which element is a noble gas? Argon. So that just expects you to know. You will get a periodic table in the exam as well. So you'll know that group 8 or 18 in the periodic table, so both are correct, 8 or 18, is noble gases. So anything on that group, anything in that group is going to be a noble gas. Tug of war, where one team pulls the other over the line, is an example of unbalanced forces. Because if it was balanced, it wouldn't move. So tug of war is this game where one team pulls the other team, okay? And there's a team pulling from this side, and there's a team pulling from this side. Now, if they were balanced, this rope wouldn't move. But if one of them pulls the other over the line, it means it's unbalanced forces. If the net force on an object is 0, then the object is so it could be stationary, or it could be moving at constant speed. Because as long as there's no acceleration, remember I said that force equals mass times acceleration. So if there's no acceleration, there's no force. That's just a little bit of extra information. You're not really expected to know that. So if there's no acceleration, there's no force, but it can still be moving at constant speed. Okay, so if we take a truck, for example, if it's moving at constant speed, then it has no acceleration. And if it's stopping completely, if it's not moving at all, then it also has no acceleration. So is at rest, which means it's not moving, or at constant velocity, that's the correct one. And remember that velocity is just speed with direction, okay? So that's all it is. So speed is distance over time, velocity is displacement over time, which is the shortest distance between 2 points. You're not expected to know that velocity is displacement over time, but you are expected to know that velocity is speed with direction. Okay, the horizontal rows on the periodic table are known as periods. Okay, and there are 7 of them, right? 7? I've got a periodic table right here. There are 7 of them. Halogens belong to group what of the periodic table? So technically speaking, 18. But if the options just show 8, then pick 8. But it is group... Oh, sorry, halogens, not noble gases. So that's 17. Or group 7 on the periodic table. The SI unit for measuring force is newtons. Okay? An object accelerates when there is a change in what? A change in speed or direction. Okay, so if an object slows down, if it's traveling at a certain speed and it slows down, that's called acceleration. And if an object is traveling around like a roundabout and it changes direction, that's also acceleration. So even if it's moving at constant speed, if it's changing direction, that's called acceleration. So acceleration happens when an object changes speed, as in slows down or speeds up, and when it changes direction or when it changes direction. What we call change in velocity, because velocity includes direction and speed as well. Number 5 is the force that opposes motion between two surfaces. So that's friction. Friction is the force. It's a contact force that exists between surfaces. And what that means, opposes motion between surfaces, is it goes against the motion. So if I'm moving in one direction, let's say for example, here we go. So that's a surface that I have. And then if I'm moving the calculator that way, the friction is moving this way. So I'm moving the calculator that way, the friction is moving that way. It opposes the direction of the motion. Now what if I go the other way? If I'm moving the calculator that way, the friction is now that way. Okay, so friction just opposes the motion. Whichever way I'm going, it opposes the motion. It's going in the opposite direction of wherever I'm going. Okay? A covalent bond forms when two atoms share electrons. Because remember, with covalent bonds, we share electrons. An example of such is hydrogen sharing with another hydrogen. Each one of them shares one electron, which satisfies their energy levels. Right, let's move on. Describe two characteristics of alkali metals. So alkali metals are in the first group of the periodic table, and as you already know, they are very reactive metals. You could also say anything about them that is metallic. So you could say they're conductive, they could say they're malleable, you could say they're ductile, you could say any of those things. But they're also known for having low density, which means they float on top of water, and you can cut them with a butter knife. You can cut them. So they have low density, they're easily cut, they're very malleable, very ductile. They have one valence electron. They have one valence electrons because they're in group 1. Anything in group 1, so starting with hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Did I miss one? Anyway, all of them have one valence electron, which means they only have one electron on the outside, which makes them highly reactive because they really want to satisfy the octet rule, which means they want to have complete outer shell, and they just have the one electron to get rid of. So that's why they're very, very reactive. How do properties of noble gases How do properties of noble gases differ from those of halogens? Well, once again, noble gases have complete outer shells. So noble gases have complete outer shells, whereas the non-noble gases, the halogens, are missing an electron. So the halogens need one more electron to complete their outer shell, so they're very, very reactive, whereas noble gases are not reactive at all. Noble gases are very, very unreactive because they are complete. They don't need anyone. They have complete electrons, number of electrons on the outside. They have complete valency. They have satisfied the octet rule. So neon, argon, xenon, krypton, what else is there? Let me try and helium. Yeah. So all of these have complete outer shells, and they don't need anything. Whereas fluorine, chlorine, bromine, iodine, all of these have incomplete outer shell. They are missing one electron, and they are highly reactive. In fact, the most reactive nonmetals are the halogens, and the most non-reactive elements are the noble gases. Okay? Explain how friction affects motion. Well, that's just the same as that one. Friction opposes the motion or the movement of the object. It's a surface, it exists between two surfaces. It's a force that exists between two surfaces that are in contact with each other, and it opposes the direction of the motion. So if I'm moving forward, friction will be moving backwards. Right, true, or correct statement. Elements in the same group have the same number of neutrons. Nope. They have the same number of valence electrons. That's all it is. They have the same number of valence electrons. Elements in the same group, they don't even have the same number of electrons. They just have the same number of valence electrons. That means electrons on the outside. Okay? Ionic bonds involve transfer of electrons. Yes, ionic bonds happen between metals and nonmetals, and the metals will transfer electrons to the nonmetals. Friction always speeds up objects in motion. Absolutely not. It slows them down. Okay, without friction, things would slip and slide and go a lot faster. But sometimes you need friction, and friction works if anything, it slows you down. It doesn't speed up the object. An object in motion stays in motion unless acted upon by an n-balanced force. So this is something that is not part of this exam, but I will answer it anyway. It's one of Newton's laws, and it's the first law, or it's Newton's law of inertia, or movement resistance, as in an object would resist movement, unless acted upon. So it will not change what it's doing. If it's staying still, it doesn't want to move, and if it's moving, it doesn't want to stay still, unless an external force acts on it. So don't worry about this question, basically, in short. Match the following terms with their definitions. Isotope. An isotope is the same version of an element, but with a different number of neutrons. So let's say, for example, helium. We have helium helium 4 and helium 5 or whatever, because then you'll have extra neutrons. So that's what we mean by an isotope. An element with stable, an atom with the same number of protons but a different number of neutrons. So that's what that is. It's C. Noble gases. Noble gases are elements that they're basically group 18 elements that have complete outer shells, and they are very unreactive. So an element with stable outer electron shell. Yep. So that's what that one is. Acceleration is change in velocity over time, or change in speed or direction over time. And unbalanced forces are forces that result in a net force or cause motion. So example of which is this box, for example. If we have 5 newtons on the left and 5 newtons on the right, those are balanced, completely balanced, zero, balanced. Whereas if I have 6 newtons on the left and 5 newtons on the right, then there will be a net force of 1 newton to the left. Okay, and suddenly they are unbalanced. So this is an example of an unbalanced force. Okay, that's all for now. I'll see you in the next video. Hello. Okay, I've got my character ready, and in this part of the video, we are going to be doing... Oh, that's wonderful. We're going to be doing the revision guide, which is basically what you guys should have by now. This guy here, we're going to be going through it and answering it, and hopefully just getting to understand this a little bit better. Okay, so have yours ready. Let's go through it, and if you need to take any notes, by all means. Okay, that's all working. That's great. Let's just change the color. Maybe something a bit more... Yeah, that dark blue looks good. Indigo? Let's go with indigo. And let's make it a bit fatter. Let's try that. Oh, that's lovely. Okay. So we're doing Unit 1, Atoms and Periodic Table, which is Lesson 2. And the periodic table, right? Okay, so the order of elements in the periodic table is based on what? It's based on the atomic number, or the number of protons. So the number of protons is also known as the atomic. That's lovely. Nice and flowy. That's wonderful. The atomic number. Which of the following elements is an alkali metal? So anything group 1 of the periodic table. So the periodic table looks like this, kind of. Yeah, kind of like that. 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Here we go. That's how it looks like, kind of. And anything in this group here is known as alkali metals. Anything in this group here is known as alkaline earth metals. Anything in group here is known as noble gases. This is the halogens. Then we've got the oxygen group, the nitrogen group, the carbon group, and so on and so forth. So group 1 is alkali metals, and that is sodium. In Mendeleev's periodic table, that's how you pronounce it, Mendeleev, because he's Russian. And his periodic table, the elements in each column had similar properties. Okay. Now he organized the periodic table according to atomic mass as opposed to atomic number, which is what we do today. But they still had similar properties, okay, in each column. So the columns are the groups. So these are the columns, okay. This way means column or group, while this way is a row or period, okay. Right, I'll try and make my handwriting better. I have a new battery in my Microsoft pen, so I should be able to make it better. Magnesium is located on the right, to the right of sodium, because magnesium has, so here's sodium and magnesium is right next to it. The reason why magnesium is to the right of sodium is because magnesium has more protons, more valence electrons, whatever you want to call it. Let's see, more protons. How is Mendeleev's periodic table arranged? We talked about that just now. We said it was arranged by atomic mass, by increasing atomic mass, which is not the same way we do it today. So today we do it by atomic number, or by the number of protons. Mendeleev left gaps in his periodic table because he knew there was supposed to be some elements in there that we hadn't discovered yet. So instead of putting in like random stuff, he just left gaps in there because he knew that none of the elements we had at the moment could fit, but he knew that in the future there was going to be some elements that would fit in there. So that's why. So it's no known elements could fit in there, and he was hoping that in the future elements would be discovered that would fit in there. That's why. Okay, moving on. Each column of the periodic table is a group, also known as a family. So this is known as a group or a family or a column, and this is known as a row or a period. And there are 7 periods in the periodic table, while there are 18 groups. Okay? Right, moving on. Noble gases are non-reactive gases or are non-reactive gaseous elements that are located in group 18 in the periodic table. Now, if you say group 8, that's also kind of acceptable. Yeah, so in the test or in the exam, hopefully there will be some choices, and there will be some choices in this sort of question. So if you don't see 18 and you see 8, then pick 8. But essentially they're the same thing. Because the reason why we say 8 is because we're not counting the transition metals in the middle. But sometimes they count them, and then it becomes group 18. So 8, 18, same thing. Group 1 of the periodic table consists of what? A highly reactive group of elements. Alkali metals. Alkali metals. The what are reactive elements in group 17? The halogens. And they are the most reactive nonmetals. So the most reactive metals are the alkali metals, while the most reactive nonmetals are the halogens. 6 elements called what? Which have some properties of metals and some properties of nonmetals. So they are metalloids. And these guys will act like metals under certain conditions, or like nonmetals under certain other conditions. So like temperature and light and so on. They're very interesting. There's 6 of them. What do alkali metals and alkaline earth metals have in common? How are they different? So alkali metals and alkaline earth metals are both metals. So let's see. Similarities. Okay, both reactive, both metals. Okay, and so they're both kind of reactive. Of course, alkali metals are way more reactive than alkaline earth metals. They're both metals, and so therefore they're both malleable and ductile and sonorous and all sorts of things. How are they different? So group 2 has 2 valence electrons on the outside, while group 1 has 1 valence electron. Alkali metals are more reactive. Okay. Yeah, I mean, we could talk about we could also say they're less, they're more dense, because these ones, alkali metals are really light, they're less dense, and they float. But we'll stop there. Now let's keep going. Atoms and the periodic table, lesson 3, bonding and the periodic table. Circle the letter of the correct answer. Semiconductors or semiconductors are elements that have large atomic masses but small atomic numbers. That makes no sense. Not form compounds, of course not. Can conduct heat and electricity under certain conditions, absolutely. And those conditions can be temperature related or light related. So it depends on whether light hits the element or whether they heat it up, their conductivity can change. So that's why they're very useful in electronics. So that's why we use semiconductors in electronics. Okay, question 2 says elements that belong to the same group have the same number of, if they are in the same group, That means they have the same number of valence electrons. So that group 1, for example, lithium, sodium, potassium, rubidium, cesium, francium, all of them have one valence electron. Even though the reactivity increases as you go down, they all have one valence electron. Okay, the three main groups of elements are metals, nonmetals, and metalloids. Most elements are... Okay, so this is an interesting question because most elements in the periodic table are metals. But in terms of numbers, like in reality, there is way more non-metals than metals. So most elements, though, if we're talking about the periodic table, most elements are metals. Okay, so if we look here, the periodic table, that is, everything here is metals. Most of the periodic table is metals. But on the ground, on Earth, and in the universe, there are more non-metals in amounts than metals. I hope that makes sense. Okay, most non-metals are brittle. And brittle is the opposite of malleable. Malleable means you can bend it. Brittle is the opposite. It means you can't really bend it so easily. Which element is a semiconductor? Silicon. Okay, and this is what we call the silly ladder. And silicon is one of those elements right there. Okay. Look at the diagram below, then answer the following questions in the space provided. How many protons does a nitrogen atom have? How many protons does a nitrogen atom have? Well, it's got 7. 7 protons. As you can see, indicated by the 7 for the atomic number. How many valence electrons does a nitrogen atom have? It's got 7 electrons, but only 5 valence electrons. Because remember, it's got 2 on the inside, and it's got 5 on the outside. So it's got 5 valence electrons. So valence electrons are the electrons on the outside that are involved in chemical reactions. It's got 5 of those. Is nitrogen reactive or stable? I'm going to go with stable. Because I'm going to assume that it's talking about nitrogen gas. And if we're talking about nitrogen gas, nitrogen has 3 covalent bonds, which makes it very, very stable. Nitrogen is used as a gas filler to protect against, like if you look at transporting of petrol in large container ships, they pump in nitrogen to get rid of the oxygen inside. So nitrogen is generally very, very stable. Nitrogen gas, that is. But nitrogen element on its own is reactive, is somewhat reactive. But again, it's not that reactive, but if we're talking about nitrogen gas, it's very, very stable. So hopefully, in the exam, that would be very, very clear as to what they mean. Okay, the element directly below nitrogen in the periodic table is phosphorus. How many valence electrons does phosphorus have? 5 as well, because it's in the same group. Will the properties of nitrogen be similar to the properties of neon or the properties of phosphorus? Explain. Okay, don't really like this question, and I'm going to explain it properly, hopefully, so please listen. So nitrogen can either be the element nitrogen, or it can be nitrogen gas. If we're talking about the element nitrogen on its own, it's in group 5, and so it hasn't satisfied the octet rule. It is going to need another 3 electrons in order to be stable. Now, if it's in group 5, it's going to be the same as phosphorus, which is in group 5. Phosphorus is right underneath it, and it also has 5 valence electrons, so it's going to have similar properties to phosphorus, right? Now we're talking about the element nitrogen. Now what about the gas nitrogen? Well, the gas nitrogen So the element nitrogen is like phosphorus, element nitrogen. However, the gas nitrogen is a bit like neon. And the reason being is because the gas nitrogen has complete outer shell. You see, it shares electrons. Sorry, 1, 2, 3, 4, 5. Yeah, 1, 2. 1, 2, 3, 4, 5. And so what happens in this case is it has 8 electrons on the outside. Oops, what did I do here? Must have done something wrong, because now it has 9. Double bond, triple bond. Nitrogen has a triple bond. Just a second. Drew an extra electron, didn't I? Here we go. That fixes things. Actually, I'm going to put this on that side. Here we go. So now it's got, as you can see, it's got 8, which satisfies the octet rule. And that one equally has 8, which satisfies the octet rule. So nitrogen gas is very stable. Nitrogen gas acts like neon, but the element nitrogen acts like phosphorus, which is in the same group, because things in the same group have the same properties. So I'm going to assume that it's talking about the element nitrogen. The properties of nitrogen be similar to those properties of neon or properties of phosphorus. I'm going to assume that it's talking about phosphorus because it's got the same number of valence electrons. Things with the same number of valence electrons, elements with the same number of valence electrons have similar properties. So like, for example, everything in group 1, all the alkali metals have similar properties. They're very reactive. Everything in group 2, the alkaline earth metals, are equally, like, they're reactive and they have similar properties, and so on and so forth. Halogens are all in the same group. They have the same number of valence electrons and they are the same reactivity, more or less. They are very reactive nonmetals and so on. And then noble gases are extremely stable. So if we're going by number of valence electrons, nitrogen is acting like phosphorus. Okay, let's keep going. Circle the letter of the correct answer. Ionic bonds form between two ions that have opposite charges, obviously. So an example of this would be Na, which is plus, Cl, which is minus. And so we'll have NaCl, which is an ionic compound. And the reason why it's very attractive or very strong is because the plus is attracted to the minus. Okay? Just like in magnets. Ions that are made of more than one atom are called polyatomic ions. So these are ions that are made from more than one atom. The word poly means many. Oops, I can do better than that. Many. And atomic just means atoms. So we have polyatomic ions. It just means an atom that is an ion that is made from more than one atom. Okay. Yeah. So let's have a look. So an example of which, for example, NH4 plus, that would be an example of a polyatomic ion. A nitrogen molecule, N2, has one triple bond. How many electrons do the nitrogen atoms have? How many electrons do they have? Do they share? Oh, do they share? Okay. Well, they share 6. Okay. There they are. They share 6. But hopefully they don't mean each. Because if they mean each, then it's 3. So once again, the question will be a lot clearer in the exam. So nitrogen molecule N2 has one triple bond. How many electrons do the nitrogen atoms share? So they both share 6 between them, and each one of them shares 3. Okay. Compared to ionic compounds, molecular compounds. So the word molecular also means covalent. Molecular compounds generally have Good conductivity, no. More chemical bonds, also no. Greater densities, also no. A low melting point, absolutely. Okay, so molecular compounds, things like plastics and such, they tend to melt quite easily, so they have lower melting points. If the statement's true, then write true. If the statement is false, change the underlined word or words to make the statement correct. Or true. The chemical bond formed when two atoms share electrons is called an ionic bond. That is false. It's not an ionic bond, it's a covalent or molecular bond. Covalent bonds usually form when a non-metal combines with a metal. That is also false. Covalent bonds form when a non-metal combines with another non-metal. If a molecule contains polar bonds, the molecule may or may not be polar overall. That is true. So polar bonds form when covalent compounds share electrons unequally. But just because a molecule has polar bonds doesn't mean that it's polar overall. It could be that they balance each other out. I wouldn't worry about this guy too much. That's just a little bit too tricky. In a polar bond, one atom pulls on the shared electrons more than the other. Yes, it's true. So if a bond is indeed polar, it just means that although there's sharing of electrons taking place between two non-metals, if they are different non-metals, one of them would probably be pulling on the electron slightly more strongly than the other, therefore resulting in a charge, in a small charge. So an example of this that you would see quite readily is in water. And so let's say in water, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Now, while hydrogen shares 1. Okay. So what tends to happen is that the oxygen has a slightly stronger pull, which makes it slightly more negative, because remember, it's pulling electrons and electrons are negative. And so the hydrogen becomes slightly more positive. And that's how that's how polar bonds are formed. It's still equal sharing, but then like one of them is pulling slightly more strongly than the other, and so it results in a charge. Okay, let's keep going. Underline, understanding main ideas. Answer the following questions in the space provided. Use the diagram to the right, at the right, to answer questions 1 to 5. Circle all the covalent bonds in the electron dot diagram. So covalent bonds are bonds between nonmetals and nonmetals. Nonmetals. So in fact, they're all covalent bonds. Okay, all of them are covalent bonds because they're all nonmetals. Okay. Which bonds shown are double bonds? Double bonds. Oxygen is a double bond, O2, or oxygen with another oxygen, that's a double bond. Which bonds shown have triple bonds? So that's the nitrogen. Okay, N2, or that. Which molecules shown have polar bonds? So polar bonds, remember, is when the sharing doesn't go exactly to plan and one of them is kind of pulling the electron slightly more strongly than the other one. So this one here is a good example. As you can see, the fluorine or the fluoride is pulling the electrons towards it a bit more strongly than the hydrogen ion is, and so it becomes slightly more negative, while the hydrogen becomes slightly more positive because the electrons are moving away from it. Okay, let's keep going. This is now mixtures and solutions. The particles in colloid remain dispersed throughout the mixture because they are extremely small. They have negative charge. They have positive charge. They are of different sizes. So they are extremely small. That is true. They are very small. But they could well be charged as well. So they could well be negatively charged, and negative charges will repel each other. But for the purpose of this exercise, colloids, like milk, have very small particles that are evenly distributed and they don't settle over time like in suspensions. Okay, so they are extremely small and that's why they are evenly distributed. You can make a solute dissolve more quickly in a solvent by doing what? By adding more solute? No. By heating the solvent? Certainly. Heating the solvent means you're giving it a bit more energy and therefore you're allowing more of these collisions to take place and more chemical reactions. The chemical reactions can take place a bit faster and dissolving can take place a bit faster. Adding ice will cool it down, so you're taking away energy. Removing some of the solvent will make the problem even worse. So no, it's by heating the solvent. All of the following will make it easier to dissolve solute in a solvent, except, so which one makes it harder? Basically, if we can reword the question here, it's saying which one makes it harder for the solute to dissolve inside the solvent. So first of all, the solute is the solid that's dissolved inside the solvent. So if we look at a cup of tea, okay, here's a cup of tea, okay, and it's rather hot, and then we've got some sugar at the bottom. Okay, that there is the solute and the solvent is the tea. Okay, so the solute is the solid, the solvent is the liquid, and then both of them together they form solution. Okay, so how do we make how do we make it harder for the solute to dissolve in the solvent? How do we make it harder? This makes it easier. This makes it easier. This certainly makes it easier. Increasing the surface area just means, like, if you have a sugar cube and you have sugar powder, the sugar powder has way more surface area than the sugar cube and will dissolve a lot faster. So adding a large amount of solute will make it slightly harder to dissolve. So that's the answer there. Some types of peanut butter settle into two layers, a solid layer and a liquid layer. These peanut butters are called what? Or are what? They are suspensions at the end of the day. Because if I take that jar of peanut butter and I leave it in the cupboard for a while and I discover that the peanuts have separated from the oil, and so you get a layer of oil on top, then they've suspended from each other, haven't they? So they become suspension. What determines whether a mixture is a suspension or a colloid? The size of the particles is a big one, because obviously the size of the particles in a suspension are bigger and they settle at the bottom, whereas the size of the particles in a colloid are much smaller and they stay dispersed, and so they don't settle, they don't separate. Okay? Particles in a what can be separated by filtration. So once again, that's in a suspension. In a solution, you can't separate them through filtration because they're dissolved inside. So if you have salt dissolved in water and you try and filter it, what's going to happen is that the salt and the water will pass through the filter because the salt is dissolved in the water. Alloy just means mixtures of metals, so this doesn't even make sense with alloys. A suspension is where you have a solid in a liquid, or well, at least one type of suspension is we have like sand and water, and that can be separated using a filter. When a solid is dissolved in water, you can separate the two by evaporation, which means evaporating the water, evaporation or distillation or boiling. Okay, so all of these are acceptable. When you have a solid dissolved in liquid, so like sugar and water or salt and water, and you want to get the salt away from the water, what you can do is you can boil the water will evaporate, and then the salt will remain behind. Another way is to, well, distillation, which is the same as evaporation, but then you cool down the water and you collect it. Another way is just boiling. Boiling is just a fancy way. Boiling is just a more layman's term for evaporation. A solution is an example of a mixture, a homogeneous mixture to be exact. Homogeneous Homogeneous mixture. Okay, homogeneous just means it is made of one substance, it's completely mixed in. Yeah, garden soil and potato salad are examples of heterogeneous mixtures. Heterogeneous mixtures, they are on the other side of the scale from homogeneous mixtures. The particles in a what are smaller than in a suspension, in a colloid, and certainly in a solution as well. They are very, very small. The solubility of gases increases when, okay, what is high and what is low? So to answer this, I'll answer it and then I'll explain it. Okay, so gases are soluble. Some gases are certainly very soluble. And if you think about fish, for example, so fish actually breathe breathe oxygen, just the same way we do. However, it's oxygen that's dissolved in water. So we breathe oxygen that's mixed in the air, right? So if I tell you to breathe in a balloon of gases that doesn't include oxygen, you would suffocate, right? You would do yourself some real harm, some serious harm, in fact, because there's no oxygen in there. Now, if you boil water and you put a fish in it, the fish would die because there's no oxygen in there. So if you heat the water, the solubility of gases decreases. It becomes harder to dissolve gases in there. Cold water is easier to dissolve gases. The other thing as well is pressure. So if you increase the pressure, it's easier to dissolve the gas. If you think about a can of Coke, okay, or a can of Pepsi, right? So here's a can of Coke, okay? And what happens is, once you open the can, you release the pressure and the gases start leaving the liquid. But when it's under pressure, it's easy for the gases to remain in the liquid. So with high pressure, it's easier to keep the gases in, and with low temperature, it's easier to keep the gases in the liquid. So both of those conditions make it easier for the gases to remain in the liquid. Okay, identify if the mixture is a solution or a suspension. Muddy water, I don't know why it's in a baby bottle. It's a bit creepy. That's a suspension. Juice. Well, it depends on the type of juice. Okay, in this example, it looks like it could be a colloid or a suspension. However, some juices are solutions. So things like apple juice, for example. Apple juice is a solution, right? Because it's very, very clear. You can see right through it. But for the most part, juices are either suspensions or colloids. So example of, especially if it contains pulp. So if it's like orange juice with the pulp, like that California brand, if you leave it for a while and the pulp separates from the rest of the juice, then it's a suspension. So it depends on the type of juice we're talking about. Ocean water is definitely a solution. It's very clear, you can see right through it, it doesn't settle, blah, blah, blah. Oil and water is a suspension. You can even see it, they are suspended from each other. And the reason why oil floats on top of water is because it's got a lower density. We are flying through these. Okay, let's go. A release of energy is a sign that an exothermic reaction has taken place. So an exothermic reaction is one where energy is released, where heat is released, and an endothermic reaction is one where heat is taken in. So a chemical change has taken place. Yes, certainly. Oxygen is present. We don't know that. A physical change has occurred. We don't know that. No. Organic chemicals are present. Maybe, but certainly a chemical change has taken place. The substance that is formed in a chemical reaction is called the product. Because remember, it's going to be reactants on one side, C plus O2 equals CO2. So these are called the reactants, and this is called the product. Okay. Oh, that's a horrible U. There we go. Which of the following is a sign that a chemical reaction has occurred? Which of the following is a sign that a chemical reaction has occurred? Change in shape? No, because if I take a piece of paper and I crumble it, like let's say for example this one here, and I crumble it, that is not a chemical reaction. So I've changed the shape and it's not a chemical reaction. Melting is not a chemical reaction either, because if you think about melting ice, well, we haven't formed a new substance. It's the same, it's just water. Dissolving, again, we haven't really formed a new substance. You can still retrieve the salt once you dissolve it in water. So formation of gas is the one they're looking for there as a sign of chemical reactions. Which of the following is not an example of a physical change? So which of the following is a chemical change? And that's rust. Crumbled paper, no. Pencil sharpening, no. We haven't formed any new substances in any of these. The only one where a new substance is formed is rust. The rate of a chemical reaction tells us about how slow or how fast the reaction is taking place. Okay, that's what a rate is. So if I tell you what is the rate at which someone's eating, you got to tell me how fast they're eating or how slow they're eating. The rate at which somebody's running, the rate at which something is happening, is how fast or slow that thing is happening. What is the difference between chemical change and a physical change? The only thing you need to know there is that a chemical change produces a new substance, a physical change doesn't. So a chemical change forms a new substance with different properties, while in physical change the material remains the same. Absolutely. In a what reaction the energy released as the products form is greater than the energy required to break the bonds of the reactants? Okay, that is quite a mouthful. But what it means is that the energy released is more than the energy being put in. So that is an exothermic reaction. In fact, that's the almost exact definition, like with H0 less than 0. So that's an exothermic reaction, so such as burning, for example. In a what reaction more energy is required to break the bonds of the reactants than is released by the formation of the product? So this is an endothermic reaction where energy is put in. Okay, decide whether each of these reactions is an exothermic or endothermic. When two chemicals mix, their temperature rises. That is exothermic. Okay. A solid burns brightly and releases heat, light, and sound. Certainly exothermic. When two chemicals are mixed, their temperature drops. That is endothermic. Two chemicals will only react if you heat them continually. That is endothermic, because they're taken in heat. Plants take in light energy, and that is also endothermic. Photosynthesis is an endothermic reaction. Okay. Okay. Let's go to the next lesson. The combination of all forces acting on an object is called the net force. Okay, so if I have a force of 7 newtons acting this way, a force of 3 newtons acting this way, and a force of 5 newtons acting down, and 5 newtons acting up, so the total net force acting on the object is going to be 4 newtons to the right. Okay, so that's called the net force. If the net force on an object is 0, then the object has balanced forces. And it could be that the object is either moving at constant speed, or it could be that the object is not moving at all. So one of those two options. Okay? But certainly the object has balanced forces. A tug of war that results in one team pulling the other across the line is an example of unbalanced forces. So think about it. If one team is pulling this way and one team is pulling this way, but this team has gone past the line, so that is an unbalanced force because these guys are pulling with a stronger force. An object that changes position relative to a reference point is in motion. That's the definition of movement. The SI unit for force is Newton. Okay. Which of the following statements is true? Frictional forces are greatest when both surfaces are rough. That is true. Let's keep going. When a truck is parked on a hill, friction pulls the truck down the hill. No. As a matter of fact, it opposes the motion of the truck. Air resistance always opposes friction. No, air resistance is itself a type of friction because air has to, it's a contact force. Air is in contact with the vehicle, and which causes friction. Friction can exist between two objects even when they are not in contact. No, friction is a contact force. It can only exist when the objects are in contact. Calculate the net force and the direction each object moves. So in this case, the net force is 0 because, I mean, I know it looks like it's not acting on the box, but it is. So it's 0, and the direction is none. It's not moving anywhere. And if you prefer, 0 newtons, but it doesn't matter because 0 is 0. Over here, we've got 25 newtons, and it's acting on the left direction. Okay. Over here, we've got 83 and 96, so that's going to be 13 newtons, and once again, that is on the left side. And over here, we've got 61 and 61, so these two balance out, but then we still have 192 newtons acting on the right side. Okay, let's keep going. Calculate the speed of a car that went a distance of 125 kilometers in 2 hours. So speed equals distance over time, which equals 125 kilometers or kilometers in 2 hours, which equals 62.5 kilometers per hour. That's the answer. How much time does it take for a bird flying at a speed of 45 kilometers per hour to travel a distance of 1800 kilometers? So another way you can do this is through the triangle. So speed equals distance over time. I'm looking for how much time. So I'm looking for time. So time is equal to distance over speed, which equals 1,800 divided by 45, which is, I don't know, 80. 1,800 divided by 45, 40. 40 hours. Don't forget the units. A football field is about 100 meters long. A football field is about 100 meters long. If it takes person 20 seconds to run its length, how fast is the person? So once again, speed equals distance over time, which equals 100 meters in 20 seconds, or 5 meters per second. If you run at 12 meters per second for 15 minutes, how far will you go? So we're looking for distance this time. So distance is equal to, look at the triangle, distance is equal to speed times time. Speed times time. Okay? The only thing is I have to be careful here because this is in meters per second and this is in minutes. So they have to be the same. So I'm going to have to change one of them. I'm going to change the minutes into seconds. How do I change the minutes into seconds? 15 minutes is how many seconds? Oh, how many seconds? So I have to go, how many seconds in a minute? 60. 15 minutes has 15 times 60, so that's 900 seconds. So that's going to be 12 meters per second, the speed, multiplied by 900 seconds, and that's going to be the distance. 12 times 900, which is 10,800 meters. Okay. The fastest train in the world moves at a speed of 500 kilometers per hour. By the way, it's in China and it's pretty impressive. You should watch the YouTube video on it. How far will it go in 3 hours? Okay, so if it goes 500 kilometers every hour, and we've got 3 hours, and how far will it go? Remember, distance equals speed times time, so it's going to be 1,500 kilometers. And that's the unit for distance, kilometers. A girl cycles for 3 hours at a speed of 40 kilometers per hour. What distance did she travel? Once again, we're looking for distance, so distance is going to be equal to speed times time. So 40 times 3, because that's in hours and that's in hours, that's fine. So it's 40 times 3, which is 120 kilometers, which is a lot for somebody on a bicycle. A train travels at a speed of 30 miles per hour. and travel a distance of 240 and travels a distance of 240 miles. How long did it take the train to complete its journey? Okay, so once again, time is equal to distance over speed. So we've got 240 miles all over 30 miles per hour. So 240 divided by 30, which equals 8 hours. After traveling for 6 seconds, a runner reaches a speed of 10 meters per second. What is the runner's acceleration? So now we're getting to a different formula. So acceleration is equal to final speed minus initial speed, which is the beginning speed, all over the time. That's the formula for acceleration. Now, some of you in my classes would be familiar with this as well. Vf minus Vi all over t, which just means final velocity minus initial velocity over time. Now, this is more accurate, to be honest, because when we're dealing with acceleration, we're dealing with velocity, not speed. But at this stage, we're not really concerned. So, yeah. So, acceleration is equal to Vf minus Vi over t. What's the final speed here? 10 meters per second, and we're assuming that they started at 0. So it's going to be acceleration is equal to 10 minus 0 all over 6, which is equal to 1.67 meters per second squared. Don't forget the squared. That's the unit for acceleration. A skateboarder traveling at 7. I'm going to make this bigger because it's that way I have more room to write. A skateboarder traveling at 7 meters per second rolls to a stop. So that's the speed initially, 7 meters per second. That's the initial speed. And then rolls to a stop. So that's 0 meters per second. That's the final speed in 3 seconds. So we've got the time, we've got the final speed, we've got whatever. So what is the skateboarder's acceleration? So that's going to be Vf minus Vi all over t. Vf just means final velocity. Vi means initial velocity. So it's going to be 0. That's the final velocity. 0 minus 7 all over 3, which equals negative 7 divided by 3, or negative 2.3 meters per second squared, which makes sense because they're slowing down. So if they're slowing down, it's going to be negative acceleration, right? If they are speeding up, it's going to be positive acceleration, but they are slowing down. So this makes sense. While traveling along a highway, a driver slows from 24 meters per second to 15 meters per second in 12 seconds. What is the automobile's acceleration? So once again, before we even start solving it, hopefully you recognize because they're slowing down, it's going to be negative acceleration. So acceleration equals final speed, which is 15, minus 24, so we already have the negative, divided by 12 seconds. So that's going to be minus 0.75 meters per second squared, because we are looking at acceleration. Let's change the color. I'm getting bored with this. I know we don't have much to go, but I'm gonna go with orange. Let's see. The velocity time graph for an object. This is a velocity time graph for an object. Use the graph to answer the questions below. Which part of the graph shows the object moving at constant speed? So this is not a velocity time. This is a speed time, which is the same for what you're doing. Which part shows constant speed? This part here, I've decided to use a color that's pretty much the same as the graph. As you can see, this part here, it's moving at 40 meters per second, and it stays at 40 meters per second for about 3 minutes or 3 seconds. So it's part B. That's what it's asking for. Which part of the graph shows the object decelerating? Decelerating means it's slowing down. So that's part C. Calculate the acceleration in the first 8 seconds. So acceleration is going to be final speed minus initial speed all over time. Okay, that's what the acceleration is. I'm not sure about this orange. I think I'll change it. let's go with dark blue. Yeah. So what is the final speed? The final, remember they're talking about the first 8 seconds. So part A. What is the final speed? The final speed is over here. It's 40. What is the initial speed? It's 0. So it's 40. Acceleration is going to equal 40 minus 0 all over the time, which is 8 seconds, which equals to 5 meters per second squared. That's what the acceleration is. The acceleration in this case is going to be the rise over the run. So hopefully you're familiar with how to do that. It's going to be equal the slope. So literally that's what we just did. That's the rise, which is 40, and that's the run, oops, which is 8. So 40 divided by 8 equals 5. Okay, the distance time graph shows 8 A's, so grade 8 student journey to the zoo. They stopped for a picnic on the way to the zoo. What time did the bus leave? 9 a.m. As you can see, 9 a.m. Or, well, 9 o'clock. It doesn't say 9 a.m., but I assume this is a 24-hour clock. So there you go, 0900. What time did they stop for a picnic? They stopped for a picnic right there, as you can see. So they stopped at 10 o'clock. At 10 o'clock. And it's 10 to 10:30. It doesn't say, show us the duration, but just to have complete answers there. So 10 to 10:30, they stopped. How far had they traveled when they stopped for the picnic? Okay, so how long did they travel for before they stopped? They stopped over here, so they traveled for all the way to here, which is 50. So they had traveled for 50 miles. Remember, the unit is miles, not kilometers. And how long did they stop for? They stopped for half an hour or 30 minutes. So it doesn't matter whether you write 30 minutes or half an hour, unless the question tells you write the answer in minutes. So 30 minutes or half an hour. What time did they arrive at the zoo? Well, so they arrived at the zoo over here. That's the end of their journey, and that was at 11:30. How far is the school from the zoo? So basically it's asking, that's the beginning, that's the end. How far is the school from the zoo? It's 90 miles, because there's the end of their journey, and it's at 90. So 90 miles. Use the graph to calculate the speed in the first hour of the journey. The first hour of the journey. So they're looking for this here. And obviously it's going to be rise over run, because speed is equal to distance over time. Now they want the distance, which is over here, and the time, which is over here. So it's going to be 50 miles in an hour. So that's going to be the speed, 50 miles per hour, because it was 50 miles divided by 1 hour. That's the speed, distance over time. Okay, that's it for this part. For the next part of the video, we're going to be doing multiple choice questions. See you soon. Hello. We are going to be answering some multiple choice questions for this part. Get ready. Please try and work out the answers before I do. So pause the video, work out the answer, try and write some notes if you need to. Okay, let's get on with it. So which of the following is a non-contact force? Well, first of all, there are 3 types of non-contact forces. So there's magnetic forces, gravitational forces, as well as electrostatic forces. So obviously magnetic forces are non-contact forces. Don't quite like this color. Let's change it. Can we change it to pencil? Oh yeah, pencil. Orange pencil? No, pink pencil. Oh, not pink. Plum. Oh, that's lovely. We'll do that. We'll do that, but we'll make it thinner. Yep, that'll do. Oh, that's lovely. Okay, we'll do that. So first of all, magnetic forces. The unit for force is newtons, obviously. Kilogram is the unit for mass, and we won't worry about energy and pressure. If two forces of 10 newtons and 5 newtons act in opposite directions, the net force is going to be, well, if we've got 5 newtons on this side and we've got 10 newtons on that side, so it's going to be 5 newtons to one side. Oh, not 50, oops. 5 newtons to one side, so it's going to be 5 newtons. A book lying on the table experiences which pair of forces? So here is a table, and we've got a book lying on the table. So which pair of forces does it experience? It's going to experience weight force acting downwards and normal force acting upwards. So that is the normal force, and that is gravitational force, also known as weight. So gravitational and weight forces. Melting ice is an example of what? A physical change, a chemical change, an exothermic or an endothermic reaction. So two answers for this one, which you don't have anything like this in the exam. You always have one answer. But for this particular question, it's two answers. And the reason why is because I'm going to explain it. So first of all, it's a physical change for sure. But also, is it endothermic or exothermic? Let's have a look. So this is ice in all its glory. Okay, it's a triangular ice. Okay, here we go. And it's melting. So in order for the ice to melt, it has to absorb heat. Heat has to go in. So it is also endothermic. Okay? Burning wood produces ash and smoke. This is, once again, a chemical change. This is not, yeah, so that's it. It's a chemical change because it is, and in fact, it's an exothermic chemical change because it releases a lot of energy and there's a new substance. Breaking glass is a physical change, obviously, because you haven't made a new substance. Rusting of iron is a chemical change as well because you've made a new substance. In an exothermic reaction, heat is released. Okay? Which of the following reactions is endothermic? Which of the following reactions is endothermic? That means it takes in energy. Which of the following is endothermic? And the answer to that is boiling water. Now, the reason why, let's go through them slowly and we'll find out why. So burning fuel, that's easy. Burning fuel is exothermic because you release a lot of energy, right? So that's exo. Let's look at condensing steam. I'm going to try and explain this briefly here. So let's say we've got proper ice, the solid version. Then we've got water, liquid water, and then so ice drops over here. Water drops, raindrops. And then we've got steam. I'm going to remove the cloud so I don't confuse you. And then we've got steam. Now that is in gas form, that is in liquid form, and that is in solid form. I shouldn't write form. Okay, so what happens when it goes from here to there? That's called melting. And this is called evaporation. Evaporation or boiling. Let's just say boiling because it'll make it easier to answer the question, although it's known as evaporation as well. So this is called condensation. Condensation. And this is called freezing. Okay, and this is what happens. In order for the solid, for the ice, to turn into a liquid, it has to gain energy because liquid particles have more energy than solid particles. And in order for the liquid to turn into a gas, it has to gain more energy. So as you go through here, this is gaining energy and gaining more energy. So this is endothermic, right? So melting is endo, and so is boiling. That is endo. You're giving it energy. However, when you turn the gas into a liquid, gas has a lot of energy. Liquid has less energy. So that is exo. The gas has to lose energy to become liquid. And likewise, the liquid has to lose energy to become solid. So both of these are exo, the bottom. Both of these are endo. So which one is an endothermic reaction? That is boiling. That's endothermic. That's exo. That's exo. And that last one is exo. I hope that makes sense. Right, combustion is an example of, combustion just means burning. Okay, combustion means burning, and that is exothermic. Which process absorbs heat? So once again, let's go back to this, absorbs heat. Which one do you think absorbs heat? Okay, so that one definitely not. That one releases heat. Freezing is also exothermic. Evaporation, also known as boiling, that is endothermic. That absorbs heat. Condensation is also exothermic. Ionic compounds usually have low melting points. They have very high melting points. Conduct electricity when dissolved in water? Yes, they do, like salt. Share electrons? No, they don't. That's molecular compounds or covalent compounds are made of nonmetals only. Absolutely not. So ionic compounds are made from metals and nonmetals. Covalent bonds form when atoms gain electrons? No, it's when they share electrons, as in the case with hydrogen and another hydrogen, or oxygen and another oxygen, where they share electrons with each other. Okay, so here's a double bond, here's a single bond, but sharing happens with covalent bonds or molecular bonds between nonmetals. Which is a property of ionic compounds? Ionic compounds are they have good conductivity in solutions. They have high melting points, so not that one, that one, that one, that one, that one, that one. Yep. Covalent compounds typically dissolve in water easily. No, they don't. Conduct electricity in a solution. No, they don't. Have low melting points. Yes, they do. And form between metals. Absolutely not. So covalent compounds typically have low melting points. So if you want to think about it, for example, plastics are covalent compounds and they melt quite easily. The number of valence electrons in an atom of oxygen is what? It has 6 valence electrons. It's in group 6, so it has 6, or 16, so it has 6 valence electrons. Atoms with 8 valence electrons are very, very stable. They are stable because they have complete outer shells. Okay, so an example of that is neon, for example, which has 8 outer shells. It doesn't need anyone. It is not reactive. Okay. Sodium in group 1 has many valence electrons. Has how many valence electrons? It has 1. It's in group 1, so it has 1. So does potassium, so does rubidium, so does cesium, blah, 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 blah. The list is long. Well, no, it's not very long. There's 7 of them. Right. The reactivity of an element depends on the number of valence electrons. Okay, the number of electrons on the outside. If it has 1, it's very reactive because it really wants to get rid of it. If it has 2, it's also reactive. It wants to get rid of the 2. If it has 3 or 4 or 5, then it's like less reactive. Then if it has 7, it just needs 1 more to be complete. So if it's really close to having a complete outer shell or fulfilling the octet rule, then it's quite reactive. Okay, let's move on. Metals are typically malleable, which means they can be bent. Okay, they can bend. Non-metals usually are brittle, which is the opposite of malleable. Like glass, for example, it breaks as opposed to bending. A property of metals is ductile. It can be drawn into wires. Which material is both conductor and an insulator under certain conditions? So that's semiconductors, and they are very, very useful for use in electric circuits. Which property describes luster? So luster just means shiny and reflective. I'm going to show you metal. Look, how do you know it's metal? It's shiny and reflective. Okay, so that's what luster means. Here is another one that is also a metal. How did you know it was a metal? Because it's shiny and reflective, right? So metals, shiny, reflective. Okay, lustrous. Substance that can be hammered into sheets. Hammered into sheets or bent is malleable. That's what it means. Can be hammered. Okay, you can change the shape of it. The atomic number of an element represents the number of protons, obviously. That's what the atomic number is, the number of protons. And that is the identity of the element. It's the number of protons. An atom of carbon has 6 protons and 6 neutrons. Its atomic mass is what? So the atomic mass is going to be both the protons and the neutrons combined. So it's going to be 6 plus 6 or 12. Elements in group 1 are called alkali metals. Elements in group 18 are called noble gases. They are non-reactive gases, also known as noble gases. Group 17 elements are known as the halogens. Halogens. Which property describes noble gases? Noble gases are non-reactive. Remember, noble gases have complete outer shells, so they are non-reactive. Speed is defined as what? Speed equals distance over time. So it is the distance covered in a certain time. So distance divided by time is sufficient. Velocity is different from speed. How? Velocity is equal to velocity equals speed plus direction. So it is in fact speed and direction as well. So it has direction added to it. So that's what velocity is. It is speed and direction combined. Direction. Speed and direction combined is velocity. Direction. An acceleration occurs when an object's speed decreases, an object's direction changes, or an object's speed increases, or all of the above. Of course, all of the above. Acceleration can happen when an object slows down, an object speeds up, or it changes direction. 3 conditions. What is the formula for acceleration? It is this one here. Final velocity or final speed minus initial velocity or initial speed all over the time is equal to acceleration. Let's keep going. A solution is a mixture, a homogeneous mixture. Yes. A mixture with visible particles. No, the particles are, you cannot see them. Non-uniform, that just means they are different. No. A suspension is clear and transparent. No, that is a solution. Has particles that settle over time? Absolutely. So what that means is if you leave it for a while, the particles will settle, will move to the bottom. And it can be filtered. A colloid, like milk, differs from a suspension because of what? The particles do not settle out. That's true. It is homogeneous. No, it's not. It's actually, in fact, heterogeneous. It contains a single phase. It cannot scatter light. It definitely scatters light, and it doesn't contain a single phase. Don't worry about the meaning of that. It is, the particles do not settle out, okay, unlike suspension. And finally, which of these is a colloid? We've already covered that so many times. Salt water is a solution. Sand and water is a suspension. Vinegar is another solution. So milk is the colloid. And with that, I will wish you the best of luck. Take it easy. Read through the book. Read through your notes. And good luck. Take care.